Hello, ladies and gentlemen. The topic of our report is on the 3D human pose estimation. I'm the presenter Zihao Zhang from the Institute of Computing Technology and the University of Chinese Academy of Sciences. The title of our paper is Weakly Supervised Adversarial Learning for 3D Human Pose Estimation from point clouds. So let's get started. Here is the outline of my presentation. As you can see, it consists of 5 parts. I will first give a brief introduction of the 3D human pose estimation problem and its relationship with virtual reality industry. Then, I will introduce the related work of our methods. Algorithm details and experiment results will be given separately then. Finally, I will draw a conclusion of our work and discuss the limitations and future works. So here is the first part, problem introduction. As we all have noticed, motion capture technology has been widely used in virtual reality and entertainment industry. For example, as the figures shown, the motion capture technology can be used to film making, such as the Siren project of Tencent and remote meeting by the holoportation project of Microsoft. With the development of consumer devices such as depth camera, accurately estimating human pose has been the fundamental and key problem, especially from only one single camera. So, why do we focus on pose estimation problems from point clouds? Compared with RGB image-based pose estimation methods, the extra spatial information provided by utilizing the depth image for 3D skeleton extraction could yield more practical solutions. Moreover, the quality of the capture point cloud is robust under different light conditions. Therefore, we still focus on the depth image-based estimation method in this work. However, there are 3 main challenges in the problem of estimating the human pose from depth image. The first one is the self-occlusion problem. As illustrated in this picture, there could be many occluded parts if you observe the subject only in one single viewpoint, and the missing body part could make trouble in estimating the accurate human pose. The second problem is a data collection problem. It is a labor-intensive and error-prone process to manually label 3D human joints from input depths or point clouds, due to the self-occlusion between the body parts as well as tedious annotation on 3D point clouds. The third problem is data representation. Some methods project 3D point clouds to 2D depth maps and use 2D convolutional neural network, which could lose the 3D context of the point clouds. Several methods adopt 3D volume or point cloud representation. However, the network may have more parameters or lose some local information. Here are our key ideas towards these challenges. To solve the occlusion problem and handle the possible ambiguity, we adopt a discriminator network to judge whether the reconstructed human joints are plausible or not, and enforce the bone length ratios. As for the labeling problem, we observe that it is easier to construct human pose dataset with 2D human joint annotations on depth image. For example, we can label 2D human joint on depth image through a line color image using an off-the-shelf RGBD camera. Though 2D human joints is closely related to 3D human pose, it can only provide weak supervision of 3D human pose. Therefore, we use the weakly supervised learning method, which enables us to fully utilize both the fully labeled data and the weakly labeled data. And to address the data representation problem, we adopt a 2-stage method, which makes it possible to use the point cloud representation and the depth map representation at the same time. The experiment results shows that our method could achieve the state-of-the-art performance. Our method can be applied to different scenarios and is robust to the variance of background and gender, which could enable the use under more virtual reality scenarios. Here are some sequences showing the results under cluttered background and different gender. As you can see from these videos, our method can generate reasonable results. Now I will give introduction of 3 related works of our methods. The first one is a viewpoint invariant feature-based method. It presents a heat map-like 2D glimpse from a depth image and use a recurrent network to predict the 3D pose in an iterative manner. This work treats the points in 3D space as depth maps and uses a viewpoint event feature to solve the occlusion problem. However, the performance of the generative 3D human pose method is largely affected by the accuracy of 2D information extraction. The second one is V2V PoseNet. It uses a 3D voxelized grid and uses a 3D convolutional neural network to estimate the per voxel likelihood for each key point. This work treats the points in 3D space as point clouds and converts it into 3D voxel grid. It uses a voxelized depth map to solve the occlusion problem. However, this method requires a clean background and is in some way time-consuming. The third one is PointNet. PointNet is a network architecture that can extract features from 3D unordered point clouds. PointNet usually takes the point coordinate and other features such as surface normals as input, which are then mapped to a higher dimensional space using a multi-layer perceptron. The main limitation of PointNet is its inability to capture the local structure of the point clouds, which makes it difficult to understand the detailed spatial pattern. To solve this problem, the authors proposed a hierarchical PointNet named PointPlate++, which defines the partitioning of point clouds using the neighborhood in Euclidean space, and applies PointNet recursively to the neighborhood. Here is the third part. I will give the details of our algorithm. So here is an overview of our proposed method. As you can see, the network consists of two modules, the point clouds proposal module and the 3D pose regression module. The point clouds proposal module aims to sample the joint-related point clouds so that the computation cost is reduced and the background is removed. The 3D pose regression module aims to estimate the 3D human pose. Using the input depth map, we first estimate the 2D human pose and use it to sample and normalize the extracted point clouds from depth image. Then we use the initial 3D pose converted from the estimated 2D pose and the normalized point clouds to predict the final 3D human pose. Now I will give a detailed introduction of these two modules. The point clouds proposal module mainly consists of two steps. We first perform 2D human pose estimation using the stacked hourglass network. The loss is set as the L2 distance between the predicted heat map and the heat map generated from the ground truth 2D joint locations. The 2D human pose can be recovered by argmax operation on the predicted heat map. Notice that the argmax operation is not continuous or differentiable, so we have to train this network separately. The 2D joint detection step can guide us to get pose-aware sampled point clouds to recover the 3D human pose. We crop the bounding box of detected 2D joints from depth map, then extract local image patches centered at the detected 2D joints. Then we estimate the position of the root joint by feeding the sampled point clouds to a tiny regression network with resonate backbone. With the root joint, the sampled point clouds can then be normalized by this formula. The 3D pose regression module aims to predict the 3D human pose through the 2D human pose and the sampled point clouds. We first obtain the initial pose by back-projecting the estimated 2D pose into 3D space and setting the depth of each joint to our estimated depth of the root joint. Then we estimate the joint offset delta Q to the initial pose. This network follows the GAN architecture and consists of the generator and the discriminator network. The generator aims to obtain the joint offsets delta Q, and the inputs of the generator network are the normalized point clouds. We feed the input to the hierarchical PointNet and obtain the joint offsets. We can update the 3D human pose by adding the joint offsets to the initial pose. The network uses the predicted 3D joint position as input and predicts whether the predicted 3D joint position is real or fake. The discriminator consists of two fully connected layers with leaky ReLU function and skip connections, and one fully connected layer with a leaky ReLU function, another fully connected layer, and a softmax function. During training, we alternatively update between discriminator D and generator G while fixing the parameters of other network. What should be noted is that during updating the generator, we use the simple yet effective indicate function to activate different loss functions based on whether the data is fully labeled or not. So here is the details of our loss function. We design a 3D post-regression network using both the fully labeled data and the weakly labeled data. The overall loss function of the generator is shown as follows, where I is the indicator function, which assesses whether the data are fully labeled data or weakly labeled data, and lambda 3D and lambda 2D are the loss weights. The variant with star means the ground truth. The first term, L3D, enforces the predicted position of the 3D joints to be close to the ground truth position of the 3D joint. We use 2D joint label supervision to learn the 3D joint location and adopt a 2D joint loss, L2D, which can reduce the searching space of the 3D human pose. It is the second term in our loss function. And to penalize illogical bone length ratios, we add a bone length ratio regularization loss to generate the 3D human pose. The bone length loss indicates that the bone length ratio computed with the predicted joints is as close as possible to the average bone length in the training dataset. The loss function of our network built upon a GAN architecture can be formulated as this. And the generator G is trained to minimize the objective function against an adversarial network D that tries to maximize it. We alternatively optimize G and D based on the min-max strategy. Here are some experiment results of our method. In our experiment, we use the ITOP dataset and Stanford EVAL dataset to evaluate our method. To evaluate the performance of our human pose estimation method, we use the following two standard metrics. The first set metrics are the percentage of correct key points, PCK, and mean average precision, MAP. The PCK value is the percentage of the detected joints out of all human joints within a given distance error threshold. The MAP is the average PCK for all human body parts. It shows the overall robustness of the pose estimation method. The other set of metrics is the mean joint error, which is defined as the mean 3D distance error of each human joint. The mean joint error can indicate the accuracy of each joint. On the right side, we show some qualitative results. The first three rows shows the results of the ITOP dataset, and the last row shows the results from the EVAL dataset. Here is the result of the self-comparison experiment. As the curve graph shows, our network design is reasonable. We also compare the performance of our methods with other state-of-the-art methods. During the comparison, we use the state-of-the-art 3D human pose estimation method, including the viewpoint invariant feature-based method, the inference embedded method, and V2V postnet. The comparison results are shown in this figure. Our method can achieve the state-of-the-art performance on the ITOP dataset compared with other 3D human pose estimation methods from point clouds. So here is the last part, conclusion and discussion. In this work, we aim to combine the image-based feature and point cloud-based feature and propose a weakly supervised adversarial learning method for predicting 3D human poses from point clouds. We use both the fully labeled 3D data and weakly labeled 2D data to train a robust pose estimation model. Our experiment on benchmark datasets show that our proposed method can achieve the state-of-the-art performance. Though inspiring results were obtained from this research, this work can be further improved to be an end-to-end framework. Specifically, our algorithm failed to fulfill the end-to-end prediction task due to the non-differentiable argmax operation in the 2D pose estimation step. Moreover, designing or utilizing other human pose representations would improve the potential of our method. For example, we can use human kinematics models with the joint angles and joint offsets and use them as the pose regression target, which could ensure that the reconstructed human joints are more plausible. That's all about my presentation.
Thanks for listening.